And welcome back to the Common Emitter Amplifier Experiment 9 Part 2. Well, I thought now we would have a look at how we can improve the gain on here. We know at the moment that the gain is the collector resistor value divided by the emitter resistor value, and that these values have been set to give us approximately 1.6 volts on here and 4.5 volts on there. And we knew in the last episode that the voltage here was nearer 5, and the voltage here was lower than 1 volt. So we didn't quite get the 2 milliamps we were aiming for, but we're in the right ballpark and it worked. So how can we increase the gain? Well, we can increase the value of that resistor, but that will change the voltage here, and we can reduce the value of this resistor so that a smaller one here and a bigger one there will give us more gain. Or what we can do is we can bypass this resistor to AC. So as far as the AC coming down here is concerned, that resistor doesn't exist. As far as DC is concerned, it's there. So it will still have the voltage across it and it will still be biased. And how do we do that? Well, we do that with a capacitor. So we do that by bringing the capacitor across the resistor. Now, AC current is going to flow down here and the DC current is going to flow down here. So effectively, that resistor is out of circuit, but that doesn't give us no resistance here. There is what often gets referred to as an intrinsic emitter resistance, which is inside the transistor, and you can't get rid of that. You can modify it, but you can't get rid of it. And that resistance is based on the temperature of the transistor and some constants. We'll have a look how we calculate it. Right, we need to know how to find little r-e, and to do that we need some formulas, or a formula. We need to know what the little r-e value is, and we need to find that from various things, 2 constants and the temperature. So let's bring it in. So the formula we need is Vt equals Kt divided by Q, where K is the Boltzmann constant, 1.38 of 10 to the minus 23, and Q is the charge on an electron, 1.60217663, 10 to the minus 19, and T is a temperature in Kelvin. And we all know that 0 degrees is 273 Kelvin, and so that 20 degrees it will be 293 in Kelvin. And then from that we know that r-e equals Vt divided by IE, and you keep them in millivolts and milliamps. And so at 20 degrees C, Vt equals that, which is 25.4 millivolts. And we know that Re therefore, r-e therefore will be 25.24 divided by 2, because that's volts over current, gives us ohms, of 12.62 ohms. We now have an emitter resistance of only 12.62 ohms. The new gain is going to be a lot higher. So let's move that up there so we can still see it a bit, and consider the old gain versus the new gain. So we'll bring that in. Right, the old gain was R collector divided by R emitter plus r-e, which was 2200 divided by 482.62 ohms, which gives us a gain of about 4.56. Now, adding the capacitor, the new gain is just RC divided by r-e. So now it's 2200 divided by 12.62, which equals 174. So, big difference. And there will be issues with our supply voltage and the gains. So that will give us, that may cause us a limit. Anyway, so let's have a look at the new circuit. Right, we're now back looking at the circuit. Let's just move that so you can see a bit better. we have 100 microfarads here across RE, but at the moment it's floating, it's not connecting. And so as you can see, we have 2 millivolts going in, $10 going out, a gain of about 5. You can't get that much better than that because we're using such low levels at the moment. And then we'll just have a quick look at the voltage points. As before, we have 0.847 on the emitter, we have 1.49 on the base, and we have 5 volts on the collector. Now let's watch what happens when we bring in the emitter resistor bypass capacitor. We might see a slight change on the input. Look at the input. We still have the 2 millivolts on the input, and we have 263 on the output. So the gain has gone from 5 to 100 and that's half of that, isn't it? 131.5. So it's 132. In our calculations, we'd calculated that R-E at 2 milliamps was about 12.5 ohms, 12 and a quarter because it's 12 and a quarter ohms. But now we can calculate it back. If we divide 2200 by 132, that's giving us an RE dash with the capacitor as well taking some effect of 16 ohms. So that just shows by putting the emitter bypass capacitor in, we can really affect the gain, but we don't affect the DC conditions. As far as the DC is concerned, the emitter resistor is still there. It's just as far as the AC is concerned, all the AC is going down here and bypassing the emitter resistor, so it's effectively not there. A word of warning, so for that we will shoot back and have a look at KiCad. Sorry, we didn't quite manage to get to the 174, we got to 132 as our R-E seemed to be higher, but it also could be that the capacitor at 100 mic isn't an exact 0 ohm impedance. It's probably a few ohms as well, and there's all these little bits here as well. There's all these connections on my experimenters board. They all add slight resistance, so it's never going to be as good as calculated. But one thing to remember, right, let's just move that out of the way over there. I'll bring in some text that I want to talk about next. So, as we know, R-E has got temperature in the equation. And if that temperature changes, then effectively this voltage changes and therefore this resistance changes. And so if we assume that the change might be 3 ohms, that could be quite a temperature range, but say for argument's sake R-E changes by 3 ohms due to an increase in temperature, then if it goes up by 3 ohms, our gain will be 144, and if it goes down by 3 ohms, our gain will be 237. So the gain changes by 93, and so we see a change by those 3 ohms of 39% in the gain. And if you want to measure that and you want your gain to be stable, then you've got a problem, because 39%, nearly 40% of a gain change due to temperature could be a problem. So what we can do is effectively keep that there so you can see it. If we take this bit away, so what we want to do is we want to keep some resistance here so that our gain isn't truly dependent on R-E. So effectively, if we cut that away and then we bring, let's just remove that. So effectively, if we bring get rid of that and that. So now we're only bypassing 330 ohms. We're leaving 150 where it is. So again, let's say that R-E changes by 3 ohms. Well, we've reduced the gain because we used to have 12.25 ohms and now we've got 150 ohms with that. So if we look at it now, we've only got a gain of 13.3, but drops by 3 ohms, we've got a gain of 13.8. So even though we've only got a gain of 13, our gain has only changed by 0.5, and so as a total change over temperature, it's 3.6%. So as you can see, we've gone from 39% down to 3.6%, and the disadvantage is we've lost some gain. But you could put a second stage in and bring more gain in. But it does mean that R-E is not a significant value in our gain calculation. So I hope you found that interesting. I won't say entertaining, but you know, you might have found it of use. You know, hit the like button. You know, please subscribe. They all help. And click on the bell for notifications. And hopefully I'll definitely see you on the next one.